All right, so we're starting in on this last bit. We're going to talk about gases for a little while. For the rest of the videos for this series, Gen Chem 1. Um, and to do this, we're going to talk about gases. Gases are important because a lot of the chemistry that we know started as gases, people working with gases and trying to figure out stuff with that. Um, and a lot of elements, all of these elements that we're highlighting here, oh shoot, highlighting here, there we go, there, hydrogen, are gases at room temperature, right? Gases are nice because their properties are mathematically related to each other. We're going to see how that goes as we do some stuff, okay? Let's look at this. Oh, what did I click? Forgive me. I don't know where my cursor is. There it is. Well, crap. Okay, here we go. Sorry. All right, gases. Gas will take the shape of its container, okay, and it takes the volume of the container. It's going to completely fill whatever container it has. Okay, it's going to completely fill the container. Additionally, gases are compressible, and this is a lot of why we have the interesting things that we can do with gases, because gases are compressible. And they're compressible because they're mostly empty space. Okay. Um, so what we're talking about by compressible is, like in the case of this, if we have this system that has a piston here and it's full of gas, and if we push this piston down, we can actually put the same amount of gas in a smaller volume. This is decreasing the volume. And what we've done is we forced the particles to be closer together, and we have, yeah, we've increased the pressure, and we'll talk about that as we do some stuff. All right. The densities of gases tend to be much smaller than liquids and solids, mostly because they're way more spread out. So typically for gas, we think of density as grams per liter. Okay. Most often with solids and liquids, right, we're talking grams per milliliter or grams per cubic centimeter. Right here, we're talking gases. Gases would be grams per liter. And the interesting thing is that while it's still an intensive property, the densities of gases are variable, and this is variable over temperature and pressure. So you can measure the density under different conditions as it goes. Okay. Also, gases, unless they react with each other, will form homogeneous mixtures with each other. And we'll see that in another video when we talk about gases mixing together. Okay. All right. So all of this starts with something called kinetic molecular theory. Okay. And in kinetic molecular theory, we're using this to explain the properties of gases. Okay. So the first thing we're saying here is they're composed of particles and they're separated by large distances, right? This is our empty space idea again. Okay. This idea was put together by Ludwig Boltzmann and I already forgot his name, John Maxwell, I think is his name. But Boltzmann and Maxwell put together kinetic molecular theory for us. Okay. Also, they say that gases are moving constantly. The particles are constantly moving, and it's random motion, but they're all in straight lines. So it's going to fly in a straight line until it hits a collision. These collisions could be with itself, or not with itself, but with the side of the container, or maybe it's going in a straight line until it hits another particle, okay? And then they'll bounce off of each other, okay? So a lot of thing about collisions. While we're thinking about collisions, we want to think about this. All of the collisions that we have when we do gases, we're going to treat them as elastic collisions. Okay. So we need a little physics sidebar here. Um, when we talk about collisions, we're thinking about if the momentum is conserved or not conserved. In an elastic collision, the momentum is conserved, which means that the particles are going to basically bounce off of each other. And the amount of momentum the particles had before collision is the same as the amount they had after the collision. Okay. So here, when we're thinking about gases, this is the situation we have where we looks like the particles are just bouncing off of each other. Okay. Those are elastic collisions. Okay. You can also think of it as like billiard balls on the table, right? They kind of just bounce off and keep going. In an inelastic collision, this is not the case. The particles tend to stick together. So they bounce off, they don't bounce, they collide together and then continue off together on their journey. Or they bounce off, but the momentum is not conserved. You've lost momentum somewhere in that it's not an immediate bounce, it's a pause and a bounce. So sticky spheres colliding with each other would be inelastic collisions because they can stick to each other for a minute. Okay. As we do that, I stumbled across some really neat looking videos as I was doing this. And this really kind of drives the point home. These are crash test videos between elastic collisions, partially inelastic and completely inelastic. And completely inelastic, the car gets stuck together. In purely elastic, the cars just bump off of each other. And in partially inelastic, there's some crushing and deformation. This is that pause during the collision, and then they bounce off of each other. Okay. But for gases, what we're talking about is we have elastic collisions. In the elastic collision, we're going to bounce off each other. The assumption we're making here is that we have no intermolecular forces. Okay, that's one of our assumptions when we're going into this. Okay. Oh yeah, that was the next thing. I probably should have just gone forward. Okay, so elastic collisions. The elastic collisions is a consequence of this, right? We have no intermolecular forces. Okay, which we kind of have an idea may not actually be true, because molecules exist, and because they exist, there should be intermolecular forces. But if you're in a reasonable conditions, then your particles are far away from each other, then you no longer feel the intermolecular forces. Okay. Our last thought here is our average kinetic energy is proportional to the absolute temperature. Okay. So how we can express this, our kinetic, nah, that's not what I want to say. Our kinetic energy, our average kinetic energy is proportional to the temperature. Here, absolute temperature, we're talking about Kelvin temperature. Okay. And it's been shown, right? We're not going to figure this out, but it's been shown the total kinetic energy for 1 mole of gas is equal to 3/2 of R times T. R is this thing called the gas constant, and we will see that later on. I'll tell you what that is. Essentially, what they've decided here, or whatever, how we figure this out, we can derive from this to say that Avogadro's number times 1/2 mass times velocity squared average equals 3/2 RT. Okay. We're not going to do anything with this. We're just kind of working our way into something here. Where we're headed is this idea of figuring out what the velocity of the gas is. Okay. This average velocity. And when we think about this, what we're doing in this part is we're looking at what's called a root mean squared velocity. Okay. Or the URMS, root mean squared. This is essentially, we can think of this as the average speed of molecules in the sample. But what this is actually is the speed of a molecule that has the average kinetic energy of the sample. Okay, so if you calculate what the average kinetic energy is, the root mean squared velocity is how fast an average particle is going in that sample. Okay, yeah, and we could calculate that out by saying the URMS is equal to the square root of 3RT divided by the molar mass in terms of kilograms per mole. Again, you might encounter this somewhere. If you go further into chemistry, you'll definitely do calculations with this. We're not going to do calculations with this. Okay. Yeah, this is, I guess, where I was supposed to do it. Okay. So what this means, though, if we think about it, is that because the kinetic energy defines the speed, we can rank things in terms of uh, their speed and relate it to their molar mass, right? That's all we're thinking about here, right? Oh, shit. Here we go, right? We're looking at velocity and we're looking at molar mass, right? So there's an inverse relationship here. Big things are going to go slower and small things are going to go faster. That's all we're getting at here with this. Okay, and we can see it here. Let's start on the right side here and look at this. At 300 Kelvin, so that's all the same temperature. Okay, this is speed on the x-axis. What we're doing is, what we're saying here is the heavier gas is moving slower. So chlorine, here's your root mean squared velocity. Okay, nitrogen, here's your root mean squared velocity. Helium, here's your root mean squared velocity. So helium is very small and it goes faster. Chlorine is a lot heavier than helium, so it moves a lot slower. Okay, so that's our first thought here. If we decrease the molar mass of gas at the same temperature, then the speed will increase. Okay. We can look at it in terms of temperature as well. If we look at the same gas, here we're looking at nitrogen gas at different temperatures, and we're measuring now the speed of the molecules. Okay, our y-axis in both these cases, how many number of molecules we have. Okay, at 100 Kelvin, we have slower molecules. At 300 Kelvin, they're a little bit faster. At 700 Kelvin, they're a lot faster. Okay, 300 Kelvin is close to room temperature. 100 Kelvin is really cold. 700 is really hot. Think of them that way. Okay, so what we're saying on this one is if we increase the temperature of the same gas, then the speed would increase as well. Okay, this is true for any gas. The exact speeds are going to be different, which is why we picked a gas to look at, right? If we did this with chlorine, we would see the same thing, although the speeds would be different, but we would see that as you heated it up, it went faster. Okay. All right. Something else to look at that deals with speed, and we're not going to do any calculations with this, but I want us to see these definitions in case we come across them, is diffusion and effusion. So really, I want us to get the two terms down. All right. Um, but, excuse me, but we're not going to do any calculations with it. What they're saying here is this is Graham's law. Okay, this is Graham and this is his law, that the rate at which the gases are diffusing or effusing is proportional to 1 over the square root of the molar mass. Okay. Um, so what this means again is bigger things are going to move slower and smaller things are going to move faster. Okay. Diffusion is mixing. Okay. And diffusion can happen in liquids too. It's just easier to see it in gases. Okay. Diffusion means if you have two gases separated here and we open the valve and let them mix, this is diffusion. Okay. Effusion is gases escaping. So here we have gas in a box on one side. The other side is under vacuum. That's key here. We have vacuum, escaping to vacuum, and it's escaping through a tiny hole. This is F fusion. Okay. The rates are the same. Okay. All right. But again, we're not going to do calculations on this. I just want us to recognize these terms. Let's see. The last thing we want to get into in this one is to talk about pressure. Pressure, we talked about this a little bit when we talked about work in the thermo stuff. Pressure is the act of a force on a unit area. So pressure is a force over a unit of area. Force, there we go. All right. Pressure can be lots of different units depending on how you're measuring it or what you're doing. The SI unit of this is atmosphere, or called standard atmosphere. Okay. This is defined by the pressure at sea level. Officially, this is a column of air that is 1 centimeter square. For the entire surface of the Earth, the atmosphere is roughly 1 kilogram of air. Okay. And this is equal to 1 atmosphere of pressure. You can't even see what I wrote there. 1 atmosphere of pressure. Okay. There are other units. Millimeters of mercury came about from reading barometers. Okay. So in a barometer, that's what this device is. You have a pool of liquid mercury, and atmosphere is pushing down on the mercury, which shoves it up the tube. And the height that the mercury is shoved is related to the pressure of the atmosphere. So you can measure the height of this and figure out what the pressure of the atmosphere is. So literally, this is a distance measurement, saying that if we had, and I don't really like how this table keeps everything in pascals, but whatever, saying that if we had 1 atmosphere of pressure, our millimeters of mercury would be 760 millimeters of mercury high. Okay, we see that here too. They said 76 centimeters, but that means the same thing. Okay. Um, Other ways of measuring: a manometer. This is more for lab gas samples. Okay. And you can measure it. The height difference from here to here is going to be your pressure, right? Or the height difference from there to there is going to be your pressure. A lot of ways nowadays, pressure is measured digitally, or you have some sort of dial you can look at where there's a needle that moves along a scale. You can measure pressure that way. Um, Other things we're going to look at here. Uh, let's see, a torr. Torr is used a lot in medicine. Torr is named after the inventor of the barometer, Evangelista Torricelli. Okay. Um, and bar is a made-up unit. Um, it's made up to be a link between pascals and atmospheres. Okay. Pascal is a small unit, so 1 bar is 1 times 10 to the 5th pascals. Okay, 1 atmosphere is 101,325 pascals. Oftentimes, chemistry will use kilopascals instead of pascals because pascals are really small. Okay. Yeah. The liquid in the barometer could be whatever you wanted. Mercury is used because it's very dense, which means you have a lot of mass per volume. Okay. And which means that it doesn't change very much when you push on it. Okay. If we made a barometer out of mercury and we had it 1 meter high of mercury, okay, to get the same measurements with a barometer made of water, we would need a 13-meter high barometer, and that's just not useful for us. So mercury is used instead. Okay. That's about it in terms of our introduction for gases. We're going to start talking about other things in a minute here. I just want us to remember that, especially in terms of pressure, we need to be able to use dimensional analysis to convert pressure units. Okay. Oh, yes. Things that we should know. And you know what I'm even going to do here? Let's keep this. And then, yes, we're going to add a slide to this so I can write this down, and we have it. Okay. Things we have to memorize to know. Why did this be like that? Okay. Is that 760 millimeters of mercury is equal to 1 atmosphere. Okay. We're memorizing these things because they are exact. Okay. Remember what exact means, right? Infinite precision, right? Which means we can ignore for figuring. Okay. So one of those is 760 millimeters of mercury is 1 atmosphere. The other one we have to know is that 1 millimeter of mercury is equal to 1 torr. Okay. So these are both things that we have to remember to do that. They both act as exact, so they're not going to affect the significant figures, but they are things that you have to know. Okay. All right. With that, I'll wrap it up. If you need me for anything, let me know. If you have any questions, let me know, and I will catch you later. Don't look up my nose. All right. Have a good one.